Hi everyone, today we'll talk about the concrete architecture analysis. Here are group members, and we have 5 topics today to talk about. Now let's move on to the first one, the conceptual architecture. As shown in Figure 1, the flight gear's conceptual architecture provides a high-level view of the various parts of the system. In this architecture, we focus on the core components of the main manager, which coordinates the interaction of other subsystems. For example, the AI and the autopilot provide data and decision support directly to the main manager, showing their influence on core operation of the stimulator. At the same time, we see 2 subsystems, the cockpit and the instrument, and the scenery and the environment, which exist in parallel representing the user interface and the world module. In addition, the navigating ad manager is connected to the scenery environment, and its role is to provide navigation assistance in the stimulated environment. The presence of the multiplayer component shows FlightGear's ability to support multi-user interactions. We update the architecture because of the constant evolution of actual development and user needs. The initial design phase, we need a clear blueprint that defines the basic function and component of the system. However, as the feature continue to added and optimized, the architecture need to be refined and adapted to accommodate more complex interaction and higher performance requirements. Next, let's move on to a more specific architecture, as shown in Figure 2. In this more detailed architecture, we can see there are 9 components within the concrete architecture for flight gear. We added 2 components. We can see that the first one is the FDM, the flight dynamic model. The flight dynamic model is the core of any flight simulation software responsible for calculating the force and the moments acting on the aircraft and determine the aircraft's response to control inputs based on its physical property. And the other one is the ATC, the air traffic control. This module manages the communication and the command of the aircraft within the airspace, replicating the role of an air traffic controller in the real world. And for the unexpected relation, we can see the red line in this graph, which indicates the new dependency we found. For example, the cockpit and the instrument, and the scenery and the environment. In the case of the airplane flight simulation, the visual reference in flight should be consistent with the data displayed by instruments, and the lighting effect in the cockpit need to be adjusted according to the time and the other condition of the external environment to make it visually realistic. Now let's move on to the second level subsystem. For the second level subsystem, we focus on the FDM. So we create a table for the dependency, like the weather service client and the main stimulation mode. Why we find there are some dependency between them. The weather is the main factor affecting the power system. Different weather condition will affect the flight states of the aircraft. So at first we ignored it when we first draw the conceptual architecture.
Okay, for subsystem analysis, we choose to analyze the flight dynamic model component. Here we can see 2 diagrams for the conceptual view and the concrete view. We both found the internal of FDM mainly consists of AI wake and LAR simulator. The initial data is input to GSBS simulator through an interface and continuously updated by test suite. Then the data will first processed by AI wake and then transferred to LAR simulator. Lastly, we used to think only of sine or cosine to express the computational part of the data. But actually, there are many other mathematical tools to correct the data. As you can see in the graph, we would use trigonometry to calculate the force and velocity or conversions between different coordinate systems. This creates a more dynamic and realistic flight experience. For the second subsystem analysis, let's look at the conceptual view at first. Last time we analyzed the client will have an ATC communication system, terminatory streaming, and the UI. Then, considering the fact that the user can interact with each other through the web, so the server can be used for networking, data synchronization, and other event manager. Then, in the context of the source code analysis and the flight dynamics interface, we developed it. So the FDI ensures that the simulated aircraft behaviors according to real-world aerodynamic principles through LAI simulator, also responding accurately to control inputs and environment changes. As you can see it in the graph, the central elements within the FDI include the aerodynamics model, flight control systems, and the weather service client. The aerodynamics model is tasked with calculating lift, drag, and other aerodynamic forces based on the aircraft's shape, angle of attack, and airspeed. These components are in close interaction with systems like the weather system, which provides real-time environment data, and they work alongside the input-output manager that processes pilot comments and sensor data. Now let's compare different dependencies between these two graphs. Except some new dependencies formed by our newly discovered subsystems, we found that only network router showed dependency to main simulation model. That is, we conclude that from the code. With the use case, let's look at the use case 1. It focuses on expressing the existence of relevant collaboration between the various components involved in real-time environment data processing when realizing AI traffic. Flight gear communicates through the ATC system and then calls the update function to update the data in real time. When the user receives a multiplayer server, the alternate paths will allow running collaborative interactions. And the second case describes after the user initializes the process, then how to trigger the flight gear to interact with the main simulation model. The upper half of this is the component will request the local data and activity the telemetry streaming for synchronized data exchange. The alternative path is using internal data to load directly. It will be more fast and easy, but also have some limitations. During our discussions, the realization of the architecture design, our communication and collaboration was generally good. Only in the early stage, there was a little problem with the task planning of the project because we didn't have a good understanding of what is the purpose and which subsystem we have to choose. Anyway, it was solved with a good communication from our group. Thanks for listening.